friends, we are going to continue our discussion on Fermi surface. We already have drawn the Fermi surface for free electrons for a two-dimensional square lattice. In this lecture, I am going to show how to draw Fermi surface when we have a periodic potential. We are going to deal with weak periodic potential such that the electrons in a periodic potential can be treated as nearly free electrons. Let us start with energy dispersion of nearly free electrons in a 2D square lattice. To get the energy dispersion of nearly free electrons, we start with the energy dispersion of free electrons in a square lattice using the empty lattice model. Note that the XM direction is lying in the boundary of the first Brillouin zone. That is why I have drawn two overlapping lines in the EK diagram along the XM direction, one red and one blue. The first band is shown in blue and the second band is shown in red. Note that the second band originally belongs to the second Brillouin zone and has been brought to the first Brillouin zone according to the reduced zone scheme. Clearly, energy of the first band along XM line is higher than energy of some portion of the second band along gamma X. For example, energy of the first band in this region is higher than the energy of the second band in this region. Same is true for certain portion of the first band along M gamma, which is higher in energy than some portion of the second band along gamma X. For example, energy of the first band in this region is higher than the energy of the second band in this region. This is known as band overlap. Band overlap can also be seen in the corresponding energy band diagrams. Blue shaded region of the first band and red shaded region of the second band overlaps in certain energy window. So far, we are just following empty lattice approximation for free electrons. Now, let us consider some weak periodic potential. How can we approximately get the nearly free electron band structure starting from the completely free electron band structure? As we did for 1D, we deform the free electron EK curves only near the Bragg planes or Brillouin zone boundaries. In these diagrams, free electron EK curves are shown by dotted lines. So these are the free electron EK curves and these are the free electron EK curves. Nearly free electron EK curves are shown by the solid lines. Note that close to the gamma point, free and nearly free electron EK curves are identical and coincide with each other, as shown here. Since XM direction lies on a Bragg plane, nearly free electron EK curves does not coincide with the free electron EK curves at all along the XM direction. Interestingly, due to weak periodic potential, overlap between the first and second band decreases because the first band moves downward and the second band moves upwards compared to the free electron EK curves. Band overlap is maximum in case of free electrons, but it decreases with increasing strength of the periodic potential. If the periodic potential is strong enough, the first and second band may not overlap at all, as shown in the third diagram. So, starting from the free electron band structure in an empty lattice, we have approximately plotted the nearly free electron band structure. We took the EK curves for free electrons and modified them only near the Bragg planes or Brillouin zone boundaries to get the EK curves for nearly free electrons. Let us see how can we draw the Fermi surface of nearly free electrons. Let us see how can we draw the Fermi surface of nearly free electrons. Again, we have to start with the free electron Fermi surface. If the free electron Fermi surface is not crossing any Bragg plane, we have nothing to do. Let us consider a case where the free electron Fermi surface shown by the dotted line crosses the Bragg planes. The free electron Fermi circle gets distorted when it crosses a Bragg plane. Let us consider this portion of the free electron Fermi circle. This is crossing the first Brillouin zone boundary at two different places. As a result, the Fermi circle gets distorted in this manner. The actual Fermi surface is shown by the solid lines. Let us complete this for the entire Fermi circle. So, this region, it will get distorted in this manner, and this region will get distorted in this manner. This region will get distorted in this manner, and this region will get distorted in this manner, and finally this region will get distorted in this manner. Thus, whenever the free electron Fermi circle is crossing the Bragg planes, we have to distort in this manner. Note that the Fermi surface is continuous in case of free electrons as shown by the dotted line. Due to the periodic potential, Fermi surface gets fragmented. Now, let me give you some justification to support my claim that the free electron Fermi circle should get distorted in this manner due to the periodic potential. As shown in the band diagram, band overlap is maximum in case of free electrons. When we have some periodic potential, band overlap decreases because the first band is moving downwards and the second band is moving upwards compared to the free electron bands. As a result, number of states occupied in the second band decreases when we have non-zero U. For example, if we consider the case of free electrons, then these many states in the second band are occupied, where the horizontal line denotes the Fermi energy. On the other hand, less number of states are occupied in the second band when we have non-zero U. As a result, when we draw the Fermi surface, area occupied in the second Brillouin zone shrinks, whereas the area occupied in the first Brillouin zone increases. The area inside the first Brillouin zone increases because the first band now has more electrons than compared to the case of the free electrons. As we did for the free electrons, we can map the regions in the second Brillouin zone back to the first Brillouin zone. In that case, this is how the Fermi surface looks like in the second Brillouin zone, and this is how it looks like in the first Brillouin zone. The dotted lines are showing the shape of the Fermi surface in case of free electrons. Let us first consider a monovalent metal. The Fermi energy lies within the first band, and it does not cross the second band anywhere, both for free electrons as well as electrons in a periodic potential. Similarly, Fermi surface is lying well within the first Brillouin zone. Since Fermi surface does not cross any Bragg plane, it is very similar to the free electron Fermi surface. Periodic potential has no effect on Fermi surface of monovalent metals. This explains why free electron theory works very well for monovalent metals like sodium, potassium, etc. Now, let us consider the case of divalent solids. Starting with the free electron band structure in empty lattice, we deform the free electron EK lines near the Bragg planes to get the nearly free electron band structure. The dotted lines in this diagram shows the free electron EK curves. The first band moves downward and the second band moves upward compared to the free electron EK curves. In case of a divalent solid, Fermi energy line crosses both the first and second band. In case of free electron band structure, we know that for sufficiently large U, the first and second band will no longer overlap. Because of no overlap, the first band has both the electrons and the second band is completely empty. Thus, for sufficiently large U, divalent atoms form an insulating solid. On the other hand, for small U, first and second band still overlaps. As shown in the figure, for free electrons, the overlap is maximum. For small U, the overlap decreases, but still there is some overlap. Because of decreasing overlap, the first band has more electrons and the second band has less electrons when compared to the free electrons. For example, in case of free electrons, these many states are occupied in the second band. However, less number of states are occupied in the second band when there is some periodic potential. As a result of band overlap, we have a metal. This explains the existence of divalent metals like beryllium, calcium, magnesium, etc. In this case, the free electron Fermi surface shown by the dotted line crosses the Bragg planes. As a result, Fermi surface gets fragmented and there is significant deviation from the free electron Fermi surface. Thus, free electron theory may not work for divalent metals. We can further generalize and say that free electron theory is expected to work only in case of monovalent metals because the Fermi surface is very similar to the free electron Fermi surface. Free electron theory is not expected to work for higher valency like divalent, trivalent or tetravalent metal because of the shape of the Fermi surface. Let us quickly look at some actual 3D metals and their Fermi surfaces. Sodium is a monovalent metal. It has a perfect free electron like spherical Fermi surface. Now let us compare the values predicted by free electron theory and actual experimental values. Gamma is the coefficient of the linear temperature dependent term of heat capacity, which can be measured experimentally by plotting heat capacity as a function of temperature. This is the value of gamma predicted by free electron theory, and this is the value of gamma measured experimentally. Experimental and free electron values are not too far from each other. Similarly, bulk modulus can be experimentally measured and estimated from free electron theory. Values are in good agreement. This is related to Hall experiment. RH is the Hall coefficient, N is the carrier density, E is the charge of electron, and C is the speed of light. This number minus 1 by RH NEC should be equal to 1, and the experimentally measured value is 1.2, which is very close. Thus, experimental values are in good agreement with free electron predictions in case of sodium because the Fermi surface is very similar to the free electron Fermi surface. Next, we look at copper. Bulk modulus predicted by free electron theory and measured experimentally differ to some extent. However, gamma and this value predicted from free electron theory and measured experimentally are in good agreement with each other. This is not surprising as copper is also a monovalent metal. Although the Fermi surface is not a perfect sphere, it has approximately a spherical shape. Next, consider the case of aluminium, which is a trivalent metal. The first Brillouin zone is completely full. This is how the Fermi surface looks like in second Brillouin zone, and this is how it looks like in the third Brillouin zone. Clearly, the Fermi surface is nowhere close to the spherical free electron-like Fermi surface. Now, let us look at some properties. Experimental and predicted gamma value match well. Experimental and free electron bulk modulus has a large difference. And we have a serious problem with Hall coefficient as this quantity is minus 0.3 if we measure experimentally. Not only the magnitude deviates from 1, the sign is also negative. In conclusion, if we have free electron like spherical Fermi surface, then free electron theory works very well. Otherwise, free electron theory may not work. Let me summarize the main concepts that helped us to understand the metals. First, we have to accept the presence of a periodic potential in a solid, and we have to solve the allowed energy values of an electron in a periodic potential. These electrons are known as block electrons. For metals, the periodic potential has to be weak. In presence of a weak potential, free electron results change to nearly free electron results. The energy values of free and nearly free electrons are identical away from the Brillouin zone boundary. Thus, we can start with free electron parabola and deform it near the Brillouin zone boundary appropriately to get the allowed energy values of an electron in a periodic potential. This is the basis of empty lattice approximation, where we plot the free electron energy along high symmetry directions in the first Brillouin zone of a reciprocal lattice. Then we deform the free electron EK curves appropriately to get the actual band structure. We have seen that it works very well for metals like aluminium. Finally, we learned how to draw the Fermi surface of free electrons and how to deform free electron Fermi surface to get the actual Fermi surface of a metal having a weak periodic potential. We have found that if the Fermi surface of a metal is free electron-like, the metal can be described using free electron theory. This happens in case of monovalent alkali metals like sodium, potassium, etc. and monovalent noble metals like copper, silver, and gold. However, for divalent and trivalent metals, free electron theory may not work. For example, we get anomalous Hall coefficient. Complications arise because of the shape of the Fermi surface. We have come to the end of our discussion related to electrons in a periodic potential. Let us take a stock of our progress so far. In the first lecture, I showed a schematic diagram of a transistor, components of which can be classified in three broad classes of materials: metals, semiconductors, and insulators. We wanted to know what determines whether a material will be a metal or an insulator or a semiconductor. Based on what we have learned so far, we can do a broad classification based on number of valence electrons per atom. In case of odd number of valence electrons per atom, we definitely have a metal. In case of even number of valence electrons per atom, we may have a metal if the periodic potential due to the underlying lattice is weak. Metallic nature is due to the band overlap. On the other hand, if the periodic potential is relatively strong, we get an insulator. In addition to the broad classification, we also know that in case of monovalent metals, free electron theory works very well because Fermi surface of monovalent metals is like free electron Fermi surface. For higher valency, free electron theory may not work. For example, in case of Hall coefficient. Complications arise because of Fermi surface. Let us also look what we do not know so far. We still do not understand the exact reason behind anomalous Hall coefficient of divalent and trivalent metals, although we know it is related to the Fermi surface. We would like to pinpoint the reason. We hardly know anything about insulators or semiconductors other than the fact that the constituent atoms have even number of valence electrons. We would like to know about them in detail.